Okay, let's look at the coding for phone measures plasticity with no hardening. And obviously we are targeting the user material subroutine in Abacus CAE. So when you talk about user material subroutine, the term UMAT is used, and UMAT is generally coming from from the user and MAT from the material. Because user material subroutines are written in Fortran language, so we're going to be covering that today. But before jumping into the implementation and coding of the phone measures plasticity theory, I would first introduce you with the UMAT subroutine if you haven't used it before. So what I will cover is what is a UMAT subroutine, how to get started with using or writing a user material subroutine, and the structure of the user material subroutine, and also the relevant variables which are involved. To explain better the concept of user material subroutine, we will consider an Abacus static analysis step. Imagine you have a rod which is made up of some linear elastic material. Young's modulus and Poisson's ratio as the properties. It is fixed from one end and you are pulling the sample from the other direction. So it's kind of a uniaxial test. So in terms of boundary conditions, we have u equals to 0 at this end, and we have a boundary condition u on the other side. So it's a static problem and we are trying to solve this. So when we define these properties, which is linear elastic properties, the geometry and the boundary condition in Abacus software, then it will first start with an increment. And to start an increment, it will find out, okay, let's start with a certain initial increment time, which again you specify in your step definition. And then it will do a global iteration and try to find out what will be the relevant strain increment for that time increment which was prescribed in the step definition. It will then call the material model with the definition of the strain increment tensor, and that material model will calculate the stresses and the Jacobian matrix. Remember, the Jacobian matrix was that partial derivative of a stress increment with respect to the strain increment tensor. Then it will solve the balance equations. All these stresses and Jacobian will be passed on from the material model to the global Abacus solver, who will solve for balance equation. In this case, the balance equation for a static case would be equilibrium equation. For static equilibrium, sum of all the forces, etc., equal to 0. And then it will check for convergence. So if it finds the equilibrium for the whole global model is satisfied, then it will update the stresses and everything, and it will go back and start a new increment. And this way your simulation will progress to the next increment until it ends at the total displacement, which is defined as the boundary condition. If it doesn't converge, which means it's a no to this, then it will again go to the global iterative solver and it will reduce the time increment, and then it will come back with a smaller strain increment tensor and then repeat the same process until it gets the convergence. So this is how it works. Now imagine if the default material model is not useful for us and we want to write our own user material subroutine, then we basically bypass this whole step here, and rather we write a UMAT subroutine where again the global solver calls the user material subroutine with the material properties, current increment of a strain, which it was doing before, also the current strain, which is the total strain at that time increment, previous stress tensor, which is coming from the previous time increment, and also any state dependent variables, which could be plastic strains or any other variables which you are storing and which are getting updated during every increment. So again, it will calculate the current stress and Jacobian. Again, Jacobian definition I have already defined before, but here I have again written it down. And then it will again solve for balance, and if it converges, updates the stresses and everything and goes to the next increment. If no, then again go back and come back with a smaller time increment. So this is the whole cycle. Now if you look at the UMAT subroutine, this is the main block of the user material subroutine in Abacus, and you can see subroutine UMAT is called with a number of variables. This is the file which is kind of a library file. You always have to include that, and then some definition, initialization or definition of different variables, that what type of variables are these. And then this is the part where you write your code. followed by a return and end. So at every integration point in your model for each element, this subroutine will be called, and your job is basically to compute all these things which are given here in the bold. So you must compute or calculate these variables. So first one is the stress tensor, second one is the state variables, which could be plastic strains, etc. in the context of von Mises plasticity, and then the Jacobian, which is the partial derivative of the stress increment tensor with respect to the strain increment tensor. Also, if you are interested, then you can also compute different types of energies like total strain energy, plastic dissipation energy, contact dissipation energy, and so on. Also, if it's a thermomechanical analysis, then you have to compute the Jacobian with respect to the temperatures as well as other things. So again, if you are interested, you can have a look at this. For the current problem, these are irrelevant for us. There are some other variables which are mentioned here. So this is the total strain at that time increment, current time increment. D strand is the strain increment tensor. For the current time increment, again, time is an array of two variables. Time 1 is the current step time, and time 2 is the total step time. So if you have multiple steps, then time 2 basically will give you the sum of all the times in all the steps prior to this current increment. D time is the time increment. Temperature is temperature value, total temperature value, and D temp is the temperature increment for this increment of time, and so on. Similarly, in addition to that, some variables are passed through abacus input file. So for example, nprops defines the number of properties which will be coming from abacus input file, and props, depending on the nprops, prop size will decide how many variables are coming as material constant. So for example, if you're using this kind of material cart for elastic material where you define the Young's modulus and Poisson's ratio, then you have two nprops. So nprops will be equal to 2, and then props 1 will be the first property and props 2 will be the Poisson's ratio in that case. Also, depending on the state variables which you are using, so let's say if you are only storing the equivalent plastic strain, which is a scalar value, then you only need one depth variable, which is the solution dependent variable. If you are storing, let's say, 6 elastic strains, 6 plastic strains, and 1 equivalent plastic strain, then this means you need a value of 13 here, and then the rest of the stuff arrays will automatically be arranged. There are some other variables here as well. For example, number of element, for which element it's being called, which integration point it's being called. So I hope this makes sense how it works. If you are defining the model, you need to make sure that you understand how abacus stores stresses and strain tensors, because if you remember from our previous parts in this course, the stress tensor can have 3 by 3 matrix. So it's a second order tensor. This means it will have 9 components. Similarly, strain will also have 9 components, but abacus uses a symmetric definition, which means the off diagonal terms, which are the shear stress values, are the same. So your matrix tensor in the matrix form is symmetric. So in that case, you only need 6 component of stresses, where stress 1 is sigma 1 1, stress 2 is sigma 2 2, stress 3 is sigma 3 3, and then so on. And so stress 6 will be sigma 2 3. Again, if you are confused with 1 1 2 2 direction, so 1 is x direction, 2 is y direction, and 3 is z direction. So sigma 1 1 will be sigma xx in contrast to any stress analysis definition, and sigma 2 3 will be sigma yx, which is a shear component of stress in yx plane. Similarly, so this means n-tens, which describes the size of the array of a stress or strain tensor or vector, is 6 for 3D elements, and this means there will be 3 direct components, 1 1 2 2 and 3 3, and then 3 shear components, and that's why you have 3 plus 3 equals to 6. So for all the 3D elements in the UMAT, this n-tens variable will be 6, which means 3 of direct component and 3 of shear components. For plane strain cases or axisymmetric elements, this will be 4, because you still have stresses. For example, for plane strain case, your strain is 0 in thickness direction, but you still have stress in the 4th direction, and that's why you have 4 components of stresses. So again, I would suggest if you are working with some other elements than 3D, then please have a look at the Abacus documentation to find out, based on your element formulation, what array size for stresses and strain should be used, or Abacus will be calling the UMAT for. Okay, so now getting back to the coding, I hope you understand what Abacus UMAT really is. So I have just copied here the template of the UMAT, which you can copy in a text file, or if you have an Intel Fortran compiler editor, then you can use that, and you can copy paste this template from the whatever version you have in your computer for Abacus. So make sure you are copying the same compatible version, because previous versions of Abacus had slightly different nomenclature as compared to the recent versions. So this is how it is, and as I explained before, this is the area where we're going to type the code. Okay, so the first thing is we need to initialize the variables, and in our case we have to define the variables such as elastic strain tensor, plastic strain tensor, the flow tensor, which tells us the direction of the flow, old stress tensor, which is coming from the previous step, and also old plastic strain tensor, which is again from the previous increment. So we need to update all these things, and for that we need to also initialize them at the in UMAT, so that it knows what these variables really mean. So that's what I have done here. E elastic is the elastic strain tensor, and tense is coming from Abacus. So for 3D case it will be 6. This is the plastic strain tensor with 6 components. This is the flow stress coming from with 6 components. These are the old stress and plastic strain components, again with 6 components in 3D context. We will also define, since we are going to use the Newton method for that residual, which I explained in the previous part. So I am defining the parameters related to Newton iteration. So tolerance is 1 exponent minus 6, which is a very small number. And we also need to find out how many number of iterations we can use in the UMAT. And we are giving a maximum value of 20 so that we can get a convergence. Now we need to also initialize the Jacobian to be 0. If you remember, Jacobian will be a 4th order tensor, so it will be a 6 by 6 matrix, and we need to assign those to 0, and also assign the material properties coming from the input file to corresponding variables, so that we can use it in Abacus. When it comes into the UMAT, it's only called prop 1, prop 2, etc. So firstly, so that's what I have done. I have defined all the DDS, DE as zeros. Then I have 3 constants in Abacus file, because we are working with von Mises theory with no hardening. So we need Young's modulus, Poisson's ratio, and yield stress. So these are the 3 variables we will be defining in the Abacus CAE or Abacus input file. And then based on our constant definition, if we say constant equals to 3 and n prop equal to 3, this means prop 1 will be the first variable, Young's modulus, prop 2 will be the second variable, Poisson's ratio, and prop 3 will be the yield strength. If we have hardening, then we will need more props, and I will show you later on if we need those in the UMAT subroutine or not. So as I told you, if we are working with finite deformation cases, then we need to use the finite deformation formulation, and Abacus has this rod-sig subroutine which can rotate the elastic and plastic strains in the forward direction. So that is what's being done here. So we call rod-sig, which transforms the state variables in the elastic and plastic zone and rotates it forward. Similarly, for equivalent plastic strain, I am also using a state variable which is 1 plus 2 times 6, right? And tensor 6 for 3D, so 6 times 2 is 12, plus 1 is 13. So equivalent plastic strain will always be state variable 13, while state variable 1 to 6 will be elastic strain, and state variables 7 to 12 will be the plastic strain tensor. And now what we do, we basically can also assign the previous stress and equivalent plastic strain to olds and old plastic variable, and that's what I have done here. So this stress which we have to update here in the UMAT, the value it has currently is from the previous increment, so we're going to store it as old as, and similarly equivalent plastic strain is stored as old plastic in this case. Now we go to the elastic predictor step, and we need to first build the elastic stiffness matrix. So we are working currently with Young's modulus and Poisson's ratio. So we need to find out the Lamé's constant. So this is the lambda and this is the mu value. And these are the standard formulas. You can find it in any linear elasticity theory book. And if you remember, the fourth order tensor looked something like this, where diagonal terms were 2 lambda plus 2 mu plus lambda for first 3 columns, and then it was mu. So that's what I have done here. So I have just assigned these values. So for example, when I is 1, this means this is 1. So 1, 1, 2, 1, and 3, 1 is assigned as this one. And then similarly, I assign for diagonal terms 2 mu plus lambda. So that's what is done, 2 times mu plus lambda. And that's a diagonal term here. And then I further assign from 4 to 6, which is this, as only mu, which is there. So again, you can have a look at that and work it out how I have done it here. But it's just transforming this into the programming language format in do loops, in the form of do loops. Okay, next, I calculate the predicted stress and elastic strain. So if you remember, the predicted stress or trial stress was the previous stress tensor plus the elasticity tensor times the increment of strain, which is again coming from Abacus solver. So that is what is going on here. Stress is the previous stress value, and then we are just multiplying it. This is a multiplication function, which is again you can use as a library function, which is this DSDDE, which is the stiffness tensor or Jacobian times the strain increment, and then you add this increment of stresses into this, and that becomes your trial value. Similarly, elastic strain is basically E elastic from previous step plus the current increment of strain. So that's a total elastic strain. Now we calculate the equivalent von Mises stress, because we have a stress tensor now, and we can use this relationship which I gave you in the previous part for the equivalent stress. Again, all the values are trial because we are not sure if it's a elastic or plastic region, because we are still in the elastic predictor step. So I use the same analogy, and if I compute the S Mises here, firstly I compute through the direct components, and then I use the next part here in the form of do loop to include the shear component of the stresses. And this is how I will get a scalar number, which is a Mises stress. So now we have to get the yield stress, which was a material property, and we stored it as Sy at the start. So we store it as SF for the time being. And now we will check if it's in the plastic region or if it's in the elastic region. And if you remember, the condition was this yield function, say sigma equivalent trial minus sigma y should be greater than 0 to be in the yielding zone. So when we check this, we define this condition here. So if S Mises, which is the trial stress, is greater than the sum tolerance value times the yield strength of the material in this case, then we need to calculate the flow direction. We need to see how far we are or out of that before we can apply the return mapping scheme, if you remember. And that flow direction was given by the derivative trial stress over the equivalent trial stress. So that's what I have done here. I compute the hydrostatic part of the stress here. I subtract the hydrostatic part from the total stress tensor, and then I divide with the Mises stress to get the flow direction for all of the 6 components of the flow direction. Okay, once we have done the flow direction, then we have to compute the incremental equivalent plastic strain. And if you remember, we'll use the Newton method. So that's, in this case, there is no hardening ideal plastic material. So I already explained ET is 0. Later on, when isotropic hardening is used, then we will use some arbitrary relationship for that. But we will come back to that once we will read the second part. Okay, so to compute the D equivalent, we need to use this residual, which I again explained in the last part, which is a function of equivalent trial strain stress, which we already know the value from the previous slide. 3 mu is, we already know the values, and we need to compute this value. That's we are after. Sigma y is the material properties, and then based on Newton method, we will find delta epsilon p, which is the equivalent plastic strain increment, using the previous value, making this residual to be 0 over 3 mu. And in this case, sigma f is sigma y, because there is no hardening. So that's what I have done here again. So from this is a Newton iteration. We compute the right hand side first, which is as measures minus 3 times mu times equivalent strain minus SF. And then we compute the D equivalent here, which is the previous value plus right hand side over 3 times mu plus ET, but in this case ET is 0, so you can ignore it for the time being. Similarly, SF is SY, and then ET is 0 because there is no hardening. So we will solve it for different values of equivalent plastic strain, and we will keep it updating as the loop goes on. Initially it's 0, and then it will keep on increasing until we get to a convergence value where the right hand side is getting smaller and smaller and is less than the some tolerance value. Again, the tolerance was 1 exponent minus 6, if you remember. We initialized it at the start of the subroutine times sy, and if it is the case, then it exits. If it doesn't exit, then it will keep on going, and we will reach to the new number of iterations equals to 20. Remember, Newton equals to 20 we have used at the start as a parameter, and in that case obviously this means that our plasticity loop has not converged. So we need to also warn the user that okay, your plasticity loop is not converged, you need to do something about it. So for that I will just say that if this thing equals to this means we have reached to the last iteration. We have a warning printed on the screen that plasticity loop failed. Once we have reached to the convergence, we need to update the stresses and strains. And by strain I mean the plastic strains and also the elastic strain. Total strains are the same which are coming from the solver. So we will first update the stresses based on this definition. I already gave you this again in the previous part. It's a function of yield stress times the flow direction plus the volumetric part, deviatoric and volumetric part. And similarly, we can find the strain tensor using this relationship. Again, I have provided you with that. So we are just updating based on the flow direction and the new computed value of this equivalent strain, and update the plasticity strain tensor using this relationship. So that's what I have done here. I will compute the stresses firstly for the 1 to 3 direction, which are the direct components, and that's flow times the SF, which is a yield stress, plus the hydrostatic stress, which we have already computed in the previous slide. Similarly, equivalent plastic strain tensor, and in this case it's again direct components, which is again using this formula. So you can see it's a straightforward use of variables. Flow is always this direction, sigma deviatoric stress tensor trial value over the equivalent stress trial value. And similarly, then I do the same for the shear components, and again the formulas are the same which are here. So they look very similar in this case. Once I have done that, I can also compute the equivalent plastic strain. In this case, I just need to add this increment which I have found from Newton iteration into the equivalent plastic strain from the previous increment. And this way I have updated the stresses, elastic strains, and also the equivalent plastic strains of 6, and 1. If you want, you can compute the plastic strain energy density, SPD, if you remember, and that is just the area under the stress strain curve, and that is what I have done here. So you can, based on the stress definition, you can find out the stress times strain over 2. The last part, which is a very most complicated part in implementing any UMAT subroutine, especially for plasticity theory, is the computation of the consistent material Jacobian. So as your material model gets complicated, your stress rate and increment of stresses become very complicated, and sometimes it becomes impossible to solve those equations. So for those cases, there are different numerical schemes which are available, which can be used to numerically estimate these Jacobians rather than accurately calculating it. And if you look at Simo and Hughes textbook, then they give you different ways of doing that. In this case, it's straightforward thing. So we have this long relationship. Again, I have just given you the final form of the relationship. If you are interested, you can have a look at any textbook. So this is the stress rate in terms of strain increment rates, and to find the Jacobian, we need to take the derivative of this with respect to is epsilon j I k l basically. So if we take this derivative, these things will go away and we will end up with these terms. So that's what I have done here. I have just defined the Jacobian based on that. So the first term, if you see, is the mu times s sigma y over s meses. So these three terms here they are at various places. So I have first calculated that. Then I calculate e over 1 minus nu, which is the k value here, because we are working with k right now, and it's very much similar to lambda. You can directly use the value of lambda as well if you already know. Minus 2 over 3, which is this, and then this thing is all EFFG variable, which is written here. Similarly, third one is this bracket here, and I have computed that here as well after simplification. So 3 times mu, which is this, times ET, which is this, because I take the LCM and then take it up, over 3 times mu plus ET, which is the denominator then. So I just simplified this relationship here. Minus 3 times, again, this whole thing is EFFG. So I first define all these and then I update this DSD DE. So for example, if you remember, and the first, if it is sigma 11, then the derivative of sigma 11 with respect to 11, 22, 33, 12, 22, 21, 23. So you have to write all the indices there, and if you start writing that, it will take a long time. So I haven't written it down, but what you can do is, for example, for the case when you have the same variables I, which means you're dealing with 1 1, 2 2 and 3 3, and in those cases you will have this term plus this term, because this term will be 0 if ij is not equal to I is not equal to j, because it's a canonical delta. So that's why whenever you have 1 1 2 2 or 3 3, which is this case here, you will have 2 times this whole thing plus this whole term here, which is, remember, this was the k minus 2 times this thing. So this is how I defined the 1 1 thing, and then you can see I have done the other definitions as well. For example, this is the term which will be having all these terms plus this term as well, in the case when you are dealing with that. So in this case, we will have this term times flow j and flow I. These are the flow terms, if you remember, in terms of ij and kl. It looks a bit confusing, but when you start writing in the indices, then hopefully you should be able to define that. If you're always confused with that, then I would suggest to use some kind of numerical technique to estimate Jacobian as well, which most of the cases people have to end up with, because this is a very highly researched topic, and Jacobian is one of the most difficult thing to implement in UMAT, especially if you're dealing with plasticity or very complicated models. So I hope I was able to clarify this. To reach to this relationship, you can look at any plasticity book, start writing them in terms of I11 indices from 1 to 6 for each I, j, k and l, and then you will end up with this, and then you will understand better how I did that. Okay, so I hope this is clear now. Now once we have done the Jacobians, we need to store all the variables as state variables, especially the strains which cannot be stored. So elastic strains, if you remember, they were from 1 to 6. So n tens is 6 for 3D cases. So state variable 1 to 6 are storing the elastic strain tensor, which is the total elastic strain tensor. Similarly, 7 to 12, 2 times 6 is 12, is storing the plastic strain tensor. And similarly, 12 plus 1, 13. So state variable 13 is storing a scalar value of equivalent plastic strain. And then return and end. So this way you have updated the stresses, all the state variables. So the abacus calls this subroutine. It computes everything, updates the state variables and stresses, goes back, checks for the global convergence, and then comes back and see if everything is fine or not. And it keeps on going until you finish your analysis. Now, what to do in the abacus input file or abacus CAE, and you need to give a name of the material. Depth variables in this case is 13, as you remember, so you have to live with 13, and these are the total number of solution dependent variables, and these are again coming from this. So you remember 6 plus 6 plus 1, which is 13 state variables. Okay, then we are storing all these state variables into different variables. So I have given those values here. 6 components of elastic strain tensor, EE, 6 plastic strain components, which are EPs, and the PEEQ is the plastic equivalent plastic strain, which is a scalar value. So when you define this in the user material subroutine, then you need to also give the properties in the material definition card. And in this case, we have 3 number of properties, which are Young's modulus, Poisson's ratio, and the yield strength. And that is given here. And this constant 3 basically signals the UMAT when it's called during the analysis that n props equals to 3. And in that case, the prop 1 is this, prop 2 becomes this, and prop 3 becomes this. So everything is automatically translated into UMAT, which is mentioned here on this slide now. So now let's create a simple 1 element input file for uniaxial loading, and we try to compare it with Abaqus default material model, because Abaqus already has a phone plasticity model. So see you on the other side.